Hello everyone. This is hypothesis testing with two samples. We're only going to study one section in this chapter, but actually part of section 8.1 as well, but 8.3 is the application we want to look at. 8.1 is just to understand the difference between independent and dependent samples. And you could read the formal definitions, but dependent is what we're concerned with, and that's when we have paired samples or matched samples. An example of independent might be the weights of two different groups of people, let's say males versus females. So they're two different groups, so they're independent. And dependent might be an example of weights, let's say, of the same person before and after a maybe diet or exercise regimen. But they're paired because it's the same person before and after. So a couple examples. Resting heart rates of 35 individuals before drinking coffee, and then the heart rates of the same individuals after drinking coffee. So since it's the same people, they're dependent. Again, it's like a before and after, or old and new, you can think of it. Old versus new. Okay, so then the next example, situation where we have test scores for 35 statistics students and then test scores for 42 biology students who do not study statistics. So they're totally two different groups of people that are independent of each other. So independent samples. And that's all we're going to study in 8.1, just understand the difference between dependent and independent. And our concern is dependent. We call it testing the difference between means. And what we want to calculate first is the difference between each matched pair. And so we're going to use D equals x1 minus x2, but the x1 will represent the before, and the x2 is going to always represent the after. Or if you like, you could think of it as old minus the new. So we calculate the difference of each matched pair, and then we calculate their mean. The mean of the differences, so we call it D bar. Conditions that we're going to assume are true, randomly selected as always, dependent samples, and the populations are both normally distributed. And if that's the case, then the sampling distribution for the differences of the means is approximated by the t-distribution. So we're always, for this case, we're always going to use the t-distribution. And therefore, degrees of freedom, n minus 1. But this is where n is the number of data pairs. So, a summary of the notation, n again, the number of data pairs, d, the difference between each of the entries for each data pair, mu sub d, the hypothesized mean of the differences, and d bar, the mean of the differences, and S sub d, the standard deviation of the differences. And we have the old-fashioned formulas to calculate d bar and S sub d, but we want to use the statistical features on a calculator. No need to go through the tedious formulas. So on page 2, we have organized test statistic. And Note that this is on our formula sheet, and it's very similar to what we've been using, except instead of x bar we have d bar, instead of just mu, mu sub d, and instead of s or sigma, s sub d. And this is on our formula sheet. There's a bunch of formulas in Chapter 8, but I highlighted the one that we're going to be concerned with. It's just this one here. You can doctor up your table and note this, and you can see that that's the formula that we just stated for the test statistic. And I'm mentioning again to use technology to find d bar and s sub d rather than the tedious formulas. Okay, so when we have to determine the hypotheses, we have to think about the relationship between the old and the new value, okay? Or before minus after. And however that's going to satisfy the claim. So essentially the sign, is it positive or is it negative? Or maybe it's equal to 0, but whatever the claim is, we have to determine what that difference represents with regards to the sign of the differences. And we are always going to state mu sub d with respect to 0. You could have it with respect to other values, but for our cases, always with respect to 0. So therefore, there's 3 possible scenarios. When you state HO and HA, it could be such that mu sub d for HO is less than or equal to 0, and therefore mu sub d would be greater than 0 for HA. It could be such that for HO, mu sub d is equal to 0, and HA would be mu sub d is not equal to 0. And then the third case would be HO is mu sub d is greater than or equal to 0, and HA would then be mu sub d is less than 0. But it's all going to be based with respect to 0, and we do have to determine if it's going to be, if the differences in the claim represent a negative difference, a positive difference, or maybe some difference or no difference at all. So we'll see that through these sets of examples. We want to state the hypotheses and identify the claim. It's almost the opposite of intuition, because then what you need to do, and we'll see this in the examples, let me point this out to you here at this stage. In the examples, you're always going to be given these matched pairs. You're going to look for a pair that satisfies the conditions of the claim. So if it's a decrease, then here's a pair that represents a decrease, 12 down to 9 before minus or after. And the difference would actually be a positive number, even though we're talking about a decrease, so it's almost counterintuitive. But what you should do is pick out a situation that represents the characteristic of the claim. Like, for example, here we want to put people through an SAT prep course, and we want to improve their test scores. So, therefore, if we take D to be the before minus the after, or the new minus the old, the old minus the new, whatever it is, we're always going to consider it to be X1 as the before or the old, and X2 to be the after or the new. And just pick a situation that fits the characteristic. Now here I'm just going to make up numbers. Alright, since it's an SAT course, we want to improve the scores. Let me say that you scored 500 the first time you took it, but then you improved, so you scored 550. See, that difference is negative, so therefore mu sub d would be less than 0. So that would go with the alternative. So mu sub d is less than 0 would be our claim. And mu sub d being greater than or equal to 0 goes with the null hypothesis. So pick a situation that fits. For example, here, nutritionist claims that this program's going to have people lose weight. Right, if you lose weight, let's say you started, pick a number. How much do you weigh? I'm going to say 160. And you lost weight, let's say you lost 5 pounds. But see, that difference is a positive number. So then mu sub d is going to be greater than 0. So when we state our HO and our HA, okay, it's strictly greater than, so it goes with the alternative, and that's our claim. And then mu sub d is less than or equal to 0 would be the null. In example C, we don't really have to make up a scenario because it's just saying it will change. This fuel additive will change the gas mileage. So the mean of the difference is not going to be 0 because it's going to change. Positive or negative doesn't matter. But that also will go with the alternative because it's not equal to. So mu sub d equal to 0 is the null. Again, everything's with respect to 0. And then this situation talks about this herbal medicine not changing the number of hours of sleep. So if it does not change, the mean of the differences will be equal to 0. So that would go with the null, because we have equality. So HA would be mu sub d is not equal to 0. Okay, it's going to be the same 5-step hypothesis testing procedure with using the critical value method as before. Only difference is really the standardized test statistic that we're going to be using. Well, I guess this should say T. But all of the other steps are going to be the same. Okay, so going through an example. This composition teacher wants to see if the program will reduce the number of errors. So look for a situation amongst the data pairs where there's a reduction in the errors. And remember, the before is x1 and the after is x2. And let me write that up here. A situation that fits a reduction. Okay, see, number 6 is just, there's no change. Number 5, there's a reduction in 4. There's actually an increase in 3, reduction and a reduction. So just pick one of the reductions. Let's say the first one, 12 minus 9. So that's going to be a negative number. So therefore, mu sub d would be less than 0. Is going to be the claim. So for HO and HA, mu sub d is less than 0, being the claim, goes with the alternative. And so mu sub d is greater than or equal to 0 goes with the null. Now what we want to do is calculate the differences for each matched pair. So x1 minus x2, so 12 minus 9, 3, 9 minus 6, 3, 0 minus 1, negative 1, 5 minus 3, 2, 4 minus 2, 2, and 3 minus 3, 0. And these are the data pieces that we want to enter in our calculator. So using the statistical feature on your calculator, we're going to find D bar and S sub D. So I'm going to use my trusty TI-30. I'm going to go to stat. Well, I'm already in stat. If I go to data though, I already have some data in there. So to clear the data, what I'll do is I'll exit stat, which is the second function. So second function, hit stat var, exit stats, press yes, and the stat disappears. So I got to go into stat mode by hitting second function and then the data key again and I want one variable. Okay, and then I'm in stat mode now, and now I enter my data. See, and my data was cleared. So to clear the data, you exit stat and then go back in. So then I enter the values: 3, frequency of 1, 3, frequency of 1, negative 1. You have to use your change of sign key to enter the negative. 2, 2, and 0 is significant. Okay, everything's entered. Go to stat variable, calculate. There's n is 6. Maybe note that as well. Let me do that after I get my S sub D and D bar. So n is 6. There's 6 data pairs. You can count them, or you can obviously see that in the table. Now let's toggle over for D bar. It's really X bar, right? 1.5. And S sub D, really S sub X, 1.6. I'm going to use a bunch of decimals here, 432. Okay, so then once we have that, we're ready to go. Our second step, critical values. Now this is a t-distribution. Remember, it's always going to be t. And the second step, the critical value. So draw the distribution. Okay. In the inequality in HA, it's less than. So therefore, oh, I made a mistake. I'm so sorry. Let's go back up here. Kind of a crucial mistake, really. 12 minus 9 is not a negative number. It's a positive number. So I got to change some things here, so I apologize for that. Alright, so let me outline them in red so you know the mistakes I made. Okay, 12 minus 9, obviously positive, so mu sub d is greater than 0. So mu sub d is greater than 0 is the claim, and less than or equal to would be the null. Okay, so therefore, since it's greater than 0, it's going to be a right-tailed test. So it's a one-tailed right test. The value of alpha was given to be 0.10. Our degrees of freedom, n minus 1. N is 6. So 6 minus 1 are 5. So let's draw the tail somewhere on the right of the mean. You can put the mean down the middle if you wanted to. But then our critical value, t sub 0, t sub c, whatever you prefer to call it. But this we look up in table 5. So in table 5, because we're dealing with the t distribution, we see the critical value for t. Let me remind you of this. Let's see, we've got alpha of 0.1 with a one-tailed test. So one-tailed 0.1 is the first column. Degrees of freedom of 5 looks like 1.476. Okay, so if you want to fill that in on the diagram, then our standardized test statistic. So d is d bar minus mu sub d over s sub d divided by the square root of n. Okay, so from our calculations, d bar was 1.5, but then mu sub d, remember, is the hypothesized population mean of the differences, which has to do with HO and HA, and it's always 0. Okay, it could be different if you wanted it to be, but our case is always 0. And then S sub d from our calculations was 1.6432 divided by the square root of n was 6. And so we've done computations like this before, so there's double check my work. We get a critical value of 2.236, and now our decision. So where is 2.236 with regards to our critical value? Well, somewhere in the rejection region. So therefore, we reject HO. And then we draw our conclusion. We're rejecting HO. HA is the claim, so the word support is going to be in our answer. And if we're rejecting HO, looks like there is enough evidence to support the claim. And remember, if you wanted to use our little table to draw the conclusion on our cheat sheet here, our table, HA is the claim, so it's the second column. We're rejecting HO, the first row. There is enough evidence to support the claim, so feel free to use that table. Alright, so then a final example. This physical education director claims that by taking a special vitamin, weightlifter can increase their strength. So look for a situation where there's an increase. You can see the majority of them are, as they should be. Otherwise, it'd be silly. If they were all decreases, why would you be testing it, right? So an increase might be, let's say, x1 minus x2. This is going to be our x1, the before or the old without the vitamin, and x2 is going to be the after or the new with the vitamin. So where there's an increase, the first one fits it, so I'll use that. 210 minus 219 is a negative number. So now that implies that mu sub d is less than 0. So in our hypotheses, HO and HA, less than 0 goes with the alternative. So mu sub d is less than 0 is the claim. And mu sub d is greater than or equal to 0 would be the null then. Alright, second step, critical value. Draw the distribution. Note that it's a one-tailed left test. because of the inequality in HA, it's less than, so it's left. The value of alpha was given to be 0.05, that's right here. We need to know the degrees of freedom. N minus 1, remember n is the number of data pairs. There's 8 of them. So 8 minus 1 is 7. And so let me mark off the tail here. Call it T sub C or T sub 0. Shade in the rejection region. And from table 5, we get that T sub C is, trust that you can do this because we've done it before. Get negative, you look it up, you get 1.895, but you have to note that it's negative because it's a left tail. Okay, and then the stats on the calculator. To get, could have done this first, but I kind of got excited. To get D bar, first off, you can note that N is 8, but then we want D bar and S sub D, and that's done by using the calculator. So calculate all these differences. 210 minus 219, that's a negative 9. So the negatives are important, of course, to enter. 230 minus 236 is negative 6. 182 minus 179, a positive 3. 205 minus 204, positive 1. 262 minus 270, a negative 8. Continuing, positive 3. Negative 3. And a 0. So those are the values we enter, the differences. These are the D's. The before minus the after, or x1 minus x2. So you enter those values into the calculator, and it gives us the mean of the differences, D bar, minus 2.375, and for the standard deviation of the differences, 4.8. I'm going to use 385. Okay, so now we can calculate our test statistic. Again, the formula, D bar minus mu sub D all over S sub D divided by the square root of N. And plugging things in, we have D bar was the negative 2.375 minus mu sub D is always 0. That's, remember, our hypothesized mean of population, mean of the differences, which is always with respect to 0 for us, and then divided by S sub D, the 4.8385 divided by the square root of N was 8. And so our standardized test statistic, double check my calculations, get minus 1.388. So then our decision. Where does minus 1.388 fall? Remember, 0's down the middle. And negative 1.3 falls somewhere before negative 1.895, so we're in the non-rejection region. So we failed to reject HO. And then our conclusion. So again, you could look at the table, but if we're failing to reject HO, okay, first off, HA is the claim, so the word support is going to be the answer. But we're not rejecting HO, so that means that HA is probably not probable. So if we cover up HA, looks like we're covering up the claim, so there's not enough evidence to support the claim. And again, feel free to use the table. Okay, so that's the end of unit test number 4. So just have a few more things to finish up for unit test 5, and that's a short test. And so come back when you're ready and for that.